The University of Illinois' Advanced Digital Science Center was established in 2009, supported by A*STAR, until 2017. At that point, we became part of NRF's CREATE program. In its time at A*STAR, ADSC generated many publications, technology licenses, and 20 spin-off ventures in Singapore and in the United States. And at CREATE, we are well posed to do more of the same. ADSC's leadership is comprised of faculty from the University of Illinois who spend significant amount of time at ADSC directing the research and interacting with NRF and with industry leaders in Singapore. 8 University of Illinois faculty participate in the CREATE program. The program also supports half a dozen or so support staff, as well as around 24 research and staff scientists and engineers and graduate students. The focal point of the CREATE program is to provide better cybersecurity for the electric power grid. The basic idea is to develop an overlay network whose devices are hardened against attacks, whose policies are designed to improve the cybersecurity of the network as best as can be done under logical and financial constraints. A number of new technologies are developed to support this particular vision, and we'll look at one right now called FPRO. For a power grid to provide us with electricity, we rely on the proper functioning of electrical substations. This is the EPIC testbed at SUTD. EPIC was designed to enable cybersecurity researchers to conduct experiments involving smart meters, generators, programmable loads, etc. EPIC has SCADA workstations, intelligent electronic devices, also known as IEDs, and programmable logic controllers. Here we see our FPRO device transparently integrated on the communication line so as to be invisible to other devices. For our demonstration, we have a device that simulates adversarial activity such as a compromised device or a remote attacker. This figure presents the key components and protocols of the substation automation and remote control in EPIC. Here's a straightforward interaction example where the control center transmits a command to an IED. First, we send a command from the SCADA workstation to the circuit breaker to close it. Next, let's see a successful attack example where there is no FPRO protection. A compromised entity within the system impersonates the control center. The compromised entity sends a syntactically correct command to the same IED. Now let's protect the system with FPRO and see its core functionality. We mesh our devices on the wires where they operate autonomously on the messages passing through them. 2 FPRO devices are used in this example, one at the SCADA workstation, the other at an IED. The FPRO device generates and verifies lightweight cryptographic evidence on the source and path of the ICS messages. Activating it is as simple as embedding the FPRO device into the connection point of the protected devices. Now let's repeat the example attack that succeeded before. The attack is accomplished when a compromised entity impersonates the control center. Validations applied by the FPRO device do not succeed and the device drops the message. Next, put the attacker outside of the substation, but give the attacker access to the VPN and its vulnerabilities and the control center's secret key. The attacker compromises the substation's VPN service and gains access to the network. The command is the same as the one sent by the compromised entity in the previous attack, but this time carries cryptographic evidence produced with the genuine secret key. The command passes through the VPN server and arrives at the IED. the FPRO device in front of the IED blocks the message again. Even though the cryptographic evidence is presented, it is blocked because its provenance does not validate. Provenance of electronic data is defined as the derivation from a particular source to a particular state of an item. In our context, we check the authentication of the message source, the message's delivery path, and the transformation of the message on the path.